4.6 Elastic potential energy and simple harmonic motion. One important type of potential energy is associated with springs and other elastic objects. Imagine a spring that is uncompressed and unstretched. When a spring is unstretched and uncompressed, the force exerted by the spring is zero. If you pull on the spring to the right, the spring will exert a force to the left. If you press or push on the spring to the left, the spring will push against this in the direction to the right. The amount of force exerted by a spring is proportional to the spring's displacement. This was known as Hooke's law, named after Robert Hooke, who discovered the relationship in 1678. Hooke's law states, the amount of force exerted by a spring is directly proportional to the displacement of the spring, and can be summarized in this equation. Where K is a special value called a spring constant. It's the constant of variation between the force exerted by an ideal spring and the spring's displacement. The way you can remember this is the tougher it is for a spring to be stretched or compressed, the larger its K value, or its spring constant. Delta X is the displacement by which this spring is either compressed or stretched. Let's try a sample problem. Let's determine the spring constant for a spring. Here we have a mass that is 0.46 kilograms, and it's suspended from the spring. As a result, the spring is compressed, or stretched rather, a displacement of delta X equals 7.9 centimeters. In order to determine the spring constant, let's examine the forces acting on the object. Let's make up negative and down positive. It doesn't matter in which direction you choose to make this. Just make sure that you're consistent with the direction from the free body diagram. Let's take a look at the sum of the forces acting on the object in the y direction. As this mass is suspended from the spring, the net force acting on the object is zero. We have the spring pulling up and the force of gravity acting down. We can replace these with equations. 0 equals negative K delta X plus mg. Let's rearrange to solve for K. If we bring this over the equal sign, we have K delta X is equal to mg. Therefore, K is equal to mg divided by delta X. The mass is 0.46 kilograms. G is 9.8 newtons per kilogram, and delta X is 0.079 meters. Remember, always convert from centimeters into meters. If you punch this into your calculator, you will get a spring constant of 57, and you will see that the units will become newtons per meter. Kind of makes sense. It's the amount of force required to stretch a spring by a given amount of displacement. Let's calculate the displacement in centimeters of the same spring when a mass of 0.75 kilograms hangs from it instead. So in this new example, the sum of the forces in the y direction is still zero. We have the force of the spring, K delta X, pulling up, and the force of gravity pulling down. In this example, we want to solve for delta X. Bring this over the equal sign, we get K delta X is equal to mg. Solving for delta X, we get delta X is equal to mg divided by K. We can sub and solve. We have 0.75 kilograms times 9.8 newtons per kilogram divided by the spring constant we calculated above to be 57 newtons per meter. If you sub this into your calculator, you should get a displacement of 0.13 meters or 13 centimeters down. Let's suppose you press up on the 0.75 kilogram mass so that it rises past the spring's unstretched position and therefore compresses the spring. Calculate the net force on the mass when the spring is compressed 5.3 centimeters. Include a free body diagram of the spring. So here we have a mass, and the force of gravity acts down on the mass. But if we press up past the equilibrium position and compress the spring is going to want to press down on the mass. So we'll have a force applied by the spring in the downward direction as well. So we're applying a force upwards, and as a result, the spring will press down and gravity will press down. Small correction, this is supposed to be force applied. So in the y direction, if we press up on the spring, the net force should be 0. Let's keep in mind that the force we're applying will be equal to the net force that the spring exerts downwards. So, looking at our free body diagram, we have negative force applied plus force of gravity, which is downward, and the force that the spring exerts in the downward direction as well. Rearranging for the net force, or the applied force rather, we have force of gravity plus the force of the spring. We can use the equations mg for gravity and k delta x for the force exerted by the spring. Subbing and solving, we get 0.75 kilograms times 9.8 newtons per kilogram plus a spring constant of 57 newtons per meter times a displacement of 0.053 meters. Subbing this into your calculator, you should get 10.4 newtons in the downward direction. So this is the net force that the spring is exerting downward. We're applying a force upwards, and as a result, the spring is going to press down. Therefore, the net force is 10.4 newtons down when the spring has been compressed by 0.053 meters. Let's determine the acceleration of the mass at this position in question C once it is released. So if you imagine, if you're compressing the spring with your hand, there's going to be a force that wants to be released. If we release this force, that mass will accelerate. The net force in the y direction will be equivalent to the mass times the acceleration. We know that the mass times the acceleration is equal to 10.4 newtons. So this will be equivalent to MA. If we rearrange, acceleration is equal to 10.4 newtons divided by a mass of 0.75 kilograms. Punch this into your calculator, you end up with an acceleration of 14 meters per second squared. Therefore, the acceleration is 14 14 meters per second squared down when the spring is compressed 0.053 meters. If the mass is moving upward, the downward acceleration means that it is slowing down due to the force of gravity and the elastic force of the spring. Imagine compressing a spring stores energy, and same with stretching a spring. When you stretch a spring, there will be stored energy within that spring. We call this elastic potential energy. This works with both springs or elastics, anything that has elastic energy. The potential energy due to the stretching or compressing of a string or a spring is called elastic potential energy and is governed by the equation elastic energy is equal to 1/2 k delta x squared. If you notice, this equation looks similar to the equation for kinetic energy. There are relationships between all of these concepts, so it is not surprising that it'll take a very similar format. Let's do an example that tests this out. As a 42 kilogram teenager balances briefly on a pogo stick, causing the spring in the stick to compress downward by 0.18 meters. Determine the elastic potential energy of the teenager. We have the mass of the teenager is 42 kilograms. We know the displacement of the spring is 0.18 meters, but we do not know the spring constant. And in order to solve this, we have to determine the spring constant first. Let's take a look at a free body diagram. Force of gravity acting down, and the spring force acting up. So the sum of the forces in the y direction is 0. So this 0 is equal to negative k delta x plus mg. We have the force of gravity downward and the force that the spring exerts in the upward direction. Bring this over the equal sign. We have k delta x is equal to mg. Solving for k, we have mg divided by delta x. We can sub and solve. 42 kilograms times 9.8 newtons per kilogram over 0.18 meters. If we sub this in, we end up with a spring constant of 2.29 times 10 to the power of 3 newtons per meter. We can use this now to calculate the elastic potential energy, which is equal to 1/2 k delta x squared. Subbing in, 2.29 times 10 to the power of 3 newtons per meter times a displacement of 0.18 meters squared. If you punch this into your calculator, you should get 37 joules. Next concept is called periodic motion and simple harmonic motion. A person usually jumps more than one time on a trampoline or a pogo stick. Often, a person will jump up and down over and over again. This motion is usually changing slightly with each jump, but suppose a jumper has a regular motion so that the height and time for each jump are always the same. Motion that repeats itself in this way is called periodic motion. Simple harmonic motion is periodic motion in which the acceleration of the moving object is proportional to its displacement. When it comes to springs, we can obtain the equation for the period of a mass on a spring with the following formula. Period is equal to 2 pi times the square root of mass divided by the spring constant. Let's try an example. When a diving board bends, the restoring force due to the board's elastic properties obey Hooke's law for an elastic material. Suppose a diver of mass 85 kilograms stands on a diving board with spring constant 8.1 times 10 to the power of 3 newtons per meter. The mass of the board is much smaller than the diver's mass, so we can ignore it. Calculate the period and frequency at which the board vibrates. Let's write down what's given. We have a spring constant of 8.1 times 10 to the power of 3 newtons per meter. And we have the mass of the diver, which is 85 kilograms. We can determine the period of the simple harmonic motion using the formula 2 pi times the square root of mass divided by the spring constant. Subbing and solving, we get 2 pi times the mass, 85 kilograms, divided by 8.1 times 10 to the power of 3 newtons per meter. If we punch this in, we should get 0.64 seconds. Therefore, the period at which the board vibrates is 0.64 seconds. If you know the period, we know that frequency and period are inverses of each other, so we can use this mathematical relationship. Frequency is equal to 1 divided by period. 1 divided by 0.64 seconds gives us a frequency of 1.6 hertz. Therefore, the diving board will vibrate with a period of 0.64 seconds or a frequency of 1.6 hertz.